time. So today we'll discuss something called simple linear regression. So it is not only only the theory session. It is not the only theory. It is not a simple theory session. Today we are going to do something hands-on with the data. Okay. Today we are going to do something hands-on with the data as well. But for that we need to understand a bit of theory before we get jump into the code. Okay. So like I explained yesterday, machine learning algorithms are divided into three broad categories: regression, classification, and clustering. So regression means regression, as I explained yesterday, is nothing but say projecting numbers into future. Say you want to project the income of a restaurant for next 3 months. So it is nothing but projecting income, projecting numbers. Income is a number, right? So you have to project the numbers in future. So that is so dealing with numbers, projecting the numbers is regression. Classification is very simple. You want to classify a credit card classifications into bad transaction and good transaction. You want to classify. You want to classify whether a class is yes or no. Some tweet is some you are doing a Twitter analysis, a sentiment analysis on Twitter. So you want to classify whether a tweet which is done is tweet is positive or negative sentiment. You want to classify that. So that is classification. So we can classify into only two classes: positive and negative, means 0 and 1. Or we can have multiple classes. So we can have 5 classes, 6 classes. So like that, multiple classes also we can have in a classification type of problems. And another problem is clustering. So clustering is something which I am showing you on the screen. Something like jumbled up, these jumbled up figures are jumbled up symbols are given to you. So it can be anything it can be anything in life. And what you are running a clustering algorithm on this kind of data, and then you are separating clusters. So stars are separated out, circles are separated out, and these blue figures are separated out, right? So you have separated out jumbled up figure into three different clusters. Okay, so this type of problem when we solve it is called clustering problem. And yesterday I explained that clustering is useful in customer segmentation and those kind of things which are very useful to online companies, like online marketing companies. So they do some kind of customer segmentation for targeted email sending and all that. Okay, so these are three main type of problems. Then let us come. Now we will be dealing with regression type of problem. Problems. As the name suggests, simple linear regression belongs to the regression category. So regression means these are observations. These are our observations. Blue dots are our observations. We have fitted a line, and I want a projection for next 3 months. Means I'll extend this line beyond the endpoint into next 3 months. Suppose it is a graph between income on y-axis and time on x-axis. Income on like I will draw and tell. So this is income, and this is time. Income and time. Okay. So this line which we have fitted is nothing but a simple regression line we have fitted. Or fitted on what? So it is fitted on this kind of observation. These are all observations. These are our separate data points. Like for this particular income at time t1, at time t1, this was our income. Okay. So like that we have plotted so many points. Once we get the point, we have fitted an approximate line, which I am showing here like this. This is the approximate line we have fitted. Okay, so now my month is going into T6, means 6th month. I suppose I am running into 6th month, and then I want income from next 3 months. So 6, 7, 8, 9. 3 months more I want, and I will extend. Then what I will do? I will simply extend this line. I will extend y-axis also, and just simply for 8th month income, if I want, I will simply connect to this and then connect like this. So this particular point which is there, which is nothing but my income in 8th month. This is all simple math we have done multiple times, right? So classification we have already understood. So you got some basic idea of now what is done in regression. Okay. So now you see a graph on this particular chart. If you are look at this chart, look at this chart. What is there on x-axis? X-axis is the number of radio advertisements. X-axis is nothing but number of radio advertisement given by any company. Okay, and y-axis is nothing but the corresponding revenue. So when we do like 50 advertisements, so this is the kind of revenue we have. When we do
Sorry
150
to,
advertisements, we have this kind of revenue.
sorry to interrupt, sir.
Yeah,
Is the presentation moving? Because for me it is frozen at classification, regression, types of
I
supervision.
think it is. Yeah, it is moving. I think, and my mobile screen, I can. No, it is frozen here.
Sir, it's stuck at classification regression.
Yeah, then you have to wait. I think some network delay or something. Okay, retry. My connection is bad. Friends network unreachable. Is still low. Okay, it is struck. Not sure, some connection problem, I think. So I'm connected and I'll check my internet as well. So internet, Google, if I search myself,
Maybe we can reshare.
reshare. No, something is changed. Some challenge is there actually. Yeah, site cannot be reached. So some internet problem at my end. So I will reconnect, disconnect and reconnect. Are you using Airtel, Malini madam?
No, sir. I am using ACT.
No, I think there might be some Airtel issue. Let me check internet again. Hold. Yeah, now it is okay. Internet
But your ID got disconnected.
ID got disconnected means I got disconnected from the meeting, right?
Yeah.
Okay.
The other one you are using in phone is connected.
Okay, so I will. Call is being recorded. Join now. So now okay.
Okay.
Now okay, right?
Yeah.
So is my screen visible now properly?
No, sir. You have to reshare the presentation.
Oh yeah, right. Sorry. We have to reshare. Share entire screen. Yeah, so it should be okay. It should be okay now, right?
Yeah.
Yeah, sir.
Yes.
Yeah. So sorry, guys. Actually, these are sorry for the interruption. These are all unavoidable problems which we cannot avoid. So anywhere like in US also, if you go, you will be having this kind of internet disconnection and all that, because sometime I do client meetings from US and European countries. Many of them tell that sorry, I got internet disconnected for 3 seconds, 5 seconds. So it is universal problem, not common to only India. Okay, so now we were talking about this graph on the right hand side. So graph is nothing but a graph, simple sketch between simple graph between number of radio ads and corresponding revenue. Because what we expect as advertisement, number of advertising or marketing, any company when increases the marketing, the corresponding revenue is expected to increase. So radio ads are given for marketing, right? So they are increasing radio ads, and as we see, the marketing revenue is increasing. This is US data, so in dollars. So if we see that the number of advertisements, say 200 in a given period of time, then said corresponding revenue is this much. Corresponding revenue is this much. Okay. So corresponding revenue is around 2.2, around 225,000 dollars. So like that, correspondingly, we have plotted so many black points. Okay, black points when we plotted, then we saw that these points are in a particular pattern, they are near to a straight line. So if I draw a dotted straight line, which I have drawn here, a dotted straight line which I have drawn here, this straight line, which I have drawn here, this straight line, if you draw properly, you will see that all points are scattered around that straight line, right? So what we have done in process, in machine learning language, we have fitted a regression line for the observations, for the samples, for the samples of data, the historical data that we had, number of aids and relationship between aid and revenue, whatever historic data we had. So on that data, we have fitted a regression line. So this is a simple regression line. Okay. So with little math background, like you guys are on math background, so this equation which I am taking my right now, y is equal to mx plus c, this must look very familiar to you. Maybe in 10th class or something, 10th class also coordinate geometry, we have learned this. So this is y is equal to mx plus c. So x is what? X is nothing but number of radio aids for this example on x-axis. What is y? Y is nothing but revenue for this example. Okay, so these are two variables, x and y. X is called dependent variable because x is called dependent variable and y is called independent variable. So y is dependent variable and radio aids are independent, and y means revenue is dependent on that, right? So what does it mean? Like our revenue, which is y variable is revenue, that is dependent on number of radio aids. So radio aid is nothing but x. So x is independent variable and y is dependent variable. So dependent variable, sometime y we call as target variable also. Target variable also it is called. Y is called target variable also. Okay, sometimes. So we call y as target variable or y as target variable or independent variable. So this is the equation. Then you will ask me a question: what is M and C? What is M and C? So if you recall maths, and even if you don't recall, it is not very tough to understand. M is nothing but the slope of this line. Slope of the line means the line which orange line which I have made here is making some angle with x-axis. X-axis it is making some angle with horizontal axis, right? So that is nothing but tan theta of that is m. M is nothing but tan theta. Okay. So this line will, if I project this backward, it will cut x-axis. So this theta angle and tan of this theta, tan theta of this angle is nothing but m. Okay, so this is m. And C means like this line is cutting on the y-axis. You see here it is cutting on the y-axis. Here one horizontal line I have made just now. So here it is cutting. So this distance from 0, this distance is nothing but this is called intercept or it is called intercept. So this is C. So M and C are two variables which define this line. So if I have value of M and C, I can very much draw this line because I know how much this line is making angle with x-axis and how much is the intercept on y-axis. So if I have M and C, I can draw this line very easily, even if I don't have any of these points, and I have only M and C. So M and C are sufficient for me to draw this line. Okay. So these M and C are called regression coefficients. So in our machine learning language, these M and C are called regression coefficients. So if I like again I see this one more here we have a chart on the left hand side. So this time we are increasing marketing budget. So this time we are increasing marketing budgets on the x-axis, and corresponding sales we are plotting in y-axis. Okay, so this time marketing budget we are increasing, but we are not telling how we are spending this marketing budget. We might be spending this marketing budget in TV advertisement, radio advertisement, or print media advertisements. Anywhere we might be spending this marketing budget. But as we increase our marketing budget, our sales also is increasing. So same story as previous graph. Same story as previous graph. So this is also, you see the dots which are points which I have plotted. The points corresponding to a particular marketing budget and sales. When we plot it, it is also approximately in straight line. Okay. So slope is understood. Slope it is nothing but the angle made by slope is nothing but the angle made by the line with x-axis. That is slope. And intercept is nothing but intercept means, suppose if I draw a line here, if I fit a line here like this, so I have fitted a regression line. So this distance from 0, this distance is nothing but it is C. It is called intercept. So now understood. So this straight line is understood. Here any questions, anybody in understanding this straight line? Because this is also a machine learning algorithm. Why it is a machine learning algorithm? Because suppose beyond 400 marketing budget of 400 lakhs, I do not have observations. Any observations I do not have. But I want marketing budget for 500 and 600 also, 600 lakhs also. So what I will do? I will simply extend this line, extend y-axis. For 500 I want, I will just touch this line here, 500. I will draw one horizontal line here. So now what I am getting? Approximately 22.5. For 500 lakhs, I don't know, like my spending was only till 400 lakhs. I was spending only till 4 crore. But my boss asked me to project the revenue for 500 and 600 also. So what I will do? I just extended this line, and just see what is it, how it is cutting on y-axis. So 22.5. For projection on 600, again I extend this line. I draw a horizontal line, then a vertical line, and I draw a horizontal line. So it is around 27 crores, right? So I got what I have done. My historical data was only from 50 lakhs till 400 lakhs. That was that I am having. But my company wanted how much will be our marketing revenue, sales. How much will be our sales for if I spend 500 lakhs per month, and if I spend 600 lakhs per month. So easily I have given the projections with the help of this regression line. So how I draw this regression line? So with these fitted lines, with these points, we have fitted a line. So for now, I have just drawn a geometrical line. So what geometrical line? So here in this class, we'll learn how to get the equation of this line, like how to get y is equal to mx plus c. What will be the value of m and c if we have these kind of points? So I will be giving you these red points are say approximately 20-25 points, right? So I will be giving you 20-30 such points, observations, a relation between x and y I will be giving you, and then I will ask you to find the relation between y and s in terms of equation. So this is called closed form equation, y is equal to mx plus c. So we'll in effect we'll be finding the value of m and c. Given the number of points, we'll have number of points, observations, number of observations we'll have. So how we'll have like x, y. XY will have now here we will have x data, and here you will have y data. So this data will be given to you, x data and y data. Number of points on x and corresponding number of points on y will be given to you. Now our job as a machine learning engineer is to find what is the value of m and c in the equation y is equal to mx plus c. So that is our job. So see how we do it. First of all, let us learn the let us learn what we call as residuals. So for this we have to learn first some couple of definitions. Okay, so now we'll get into some definitions. So what is the first definition is what is residual? So suppose I have this thick black line which I am saying this is our regression line. Suppose this is our regression line. Okay, this is our regression line. These blue dots which I have made here, 4-5 blue dots, these are our nothing but observations. So first blue dot is the relationship between x and y. Second blue dot also relationship between x and y. So what is the value of x for second dot? Around you see second dot is cutting around here. Here it is cutting, and it is cutting here. So x value is approximately 2.75, and y value is approximately 6.8, right? Y value is around 6.8 and x value is around 2.5. So that's where is the second dot. Then similarly we have third dot, fourth dot, and fifth dot. These 5 dots were given to you. Then one intelligent gentleman fitted this black thick line on this. So this is our regression line. So this regression line we have fitted. But you see, that actual observations are still away from the regression line. Because if I do an exact fit means will go like this. Okay, so it will be very curvilinear. Exact fit will be very curvilinear. And this exact fit will be this will be a very complex equation. Maybe x to the power 3 or x to the power 4 in this equation will go up to x to the power 2, x to the power, this is not x to the power 2. This is definitely 4 x to the power 4 and above. So this equation is very complex. But what we have done? We have done a simplified model. What simplified model? So this straight line, our straight line is there, black straight line. This is the approximation we have done. So approximately I have fitted a straight line here. Approximately I have fitted a straight line, and I'll remove all these dots. So approximately I have fitted a straight line. So I have made a model. In machine learning language, I have made a mathematical model. Mathematical model of what? Mathematical model for representing these observations. So why I make a mathematical model? I have observations only till 5.25. See, up to 5.5 only I have observations. If I want projection beyond 5.5, say 6, 7, 8, I want projections. What will the value of y when if I increase value to, if I increase the value of x to 6, 7, 8, 9. So this line I will simply extend, as I showed you earlier. I'll simply extend this line and get the value of y. So that is why for making future projection, I have made the models. Okay. So now you still see that there is a difference between actual and what model you have made. So if you see actual is this, and your model is giving this value, right? This value is giving the model and actual. So see, this point is still red, which I am plotting. This is still gap. For third point, this is the actual, and this is the. So this particular thing is still gap. Okay, no? So this gap between actual and the model, the values given by the model and the values given by the actual values and the actual values given by the model, this gap we called as we call it residuals. Why we call this residual? Because we are not able to with 100% accuracy, we are not able to represent these observations. I told you, because 100% accuracy, if I have to fit a model, so model will go something like this. Like this model will go, right? Which will be very complex model. It will not be useful to us. And getting such a model will be very complex also mathematically. So what we have done, we have fitted a straight line. So we have fitted a straight line. So there is a difference between, for same value of x, that is 3.7, I have two values now. One is observed value, actual observed value, which is blue dot. Actual observed value is nothing but this actual observed value, and this is the actual observed value, which I am doing here. And this is the model value. This is model value, है ना? So model value. So the model value means value given by model. So there are two values. So difference between observed value and the model value is called residual. So this concept will be useful to us. How? We'll see it in later slides. Okay. So what we do later on, this residual in other, there is one more same diagram I have drawn once again. See, x-axis 100, 200, 300 points. Y-axis there are some points 10 to 30. Then B0 is our nothing but our intercept. B0 is intercept. Angle is also shown. This is the angle. See, this is the angle shown. This is the angle. This is the angle made by. This is the angle. This is the angle made by this line with the horizontal line. Right? This is the angle. And this is what this particular thing is your intercept. So this line where, so all things are shown. So sometimes residuals in our more technical terms, we call it as a error term. We called it as a error term. Residuals are also called error terms. Now you see all these, what are these? All these points, all these points, these points, these points, these points, all these are actual observations. So difference between actual observation and the model line is called error term. Okay, so now however, now with this different notation, I am representing intercept as B0 and the angle as I am representing B1. So see, this is our equation in more technical terms, more mathematical or more exact terms. This is the equation of our regression line. So we used to call it y is equal to mx plus c. Y is equal to mx plus c. So now M is represented by B1, C is represented by B0 plus, because there is a error term. Why? To get the exact value of Y, I have to add a error term also in this equation. So E is added here. Error term E is added here. You see, error term E is added. So now our equation is slightly modified. Y is equal to a constant term plus another constant term B1 into X plus error term E. Okay. So our aim as a machine learning engineer is to minimize this error. The more is this error means our model will not be exactly representing the observed points. But if error is very close to 0, then the value of Y will be very close to value given by our model will be very close to the observed point. So this equation, this line equation Y is equal to B0 plus B1X plus error term. So this is nothing but it is called our model. This is our linear regression model. Okay, I multiple times I have told you now. This is our LR model. This is our linear regression model, right? So what we want to do, we want error terms as close as 0 to the possible. Because if it is close to 0, our model will very truly represent the observed points. So this is how we, in more technical terms, we define it. So see error term. Error term means very simple. Y is the residual, Y is the Yi is the observed value and Yi cap. This is Yi cap. This is Yi cap. This is actual. Yi is actual and Yi cap. So difference between actual and the difference between actual value and the observed the value given by model is called your error term. And what is residual sum of squares? So all the error terms, like for all these points, there are number of points represent here, right? So for first point I am representing error term as E1. Second point error term E2. And for nth point I am representing error as En. If I sum up everything, square and sum up everything, I call it residual sum of squares. So this is a very important concept in regression modeling. Residual sum of squares. So it is very simple. For every observed point, we calculate the error, we square it, and we sum it. The total sum is called residual sum of squares. It is a very important concept. How we'll see how it is an important concept. If RSS is more, residual sum of squares is more, that means our model is not correct. Our model is not exact. We want residual sums of square as very less, very close to 0. So why we have squared it? Because you see in this blue line, if you see this blue line, some points are above y-axis, above the line, and some points are below the line. So for the points which are above the line, kind of like of this point, which are above the line, the error term will be positive. The points which are below like these points, below points, this point. So error term will be negative. So some error will be positive and some error will be negative. Okay. So if we don't square it, then positive and negative will cancel off, right? So but still both are errors, right? Positive error is also error and negative error is also error. We want both positive and negative errors both to be as close to the 0 as possible. So we want only the magnitude. We don't want the sign. So what we do? We square off them. So we square them. So even square. So like this, we put equation like this. We square each term so that even if it is negative, it becomes positive. Square of a negative number is a positive number, right? Square of a negative number is always a positive number. So let it be whether it is a positive error or a negative error. We square it and sum it to find out our magnitude of our error. Residual sum of error is nothing but error. So how we find it out? Calculate the error term in absolute terms with sign. In absolute terms, whether it is positive or negative, calculate the error, make a square, and then add all the errors you add up from E1 to En. So that is our residual sum of errors. I'm stopping here for a moment, and if any questions, any understanding problems till this, Is it easy? Anybody? I want you guys to speak up. I want you guys to speak up. Ujjain Engineering College students, is it easy for you so far?
Yes, sir.
Madam?
Yes, sir.
Yes.
Yes, sir. Yes, sir. It is.
So very
Understand.
easy. So just now we have I have explained you two concepts. One is what is regression line. Then I have explained you what is B0, what is B1. B0 is nothing but the constant term which I have shown here, that circle here. B1 I have shown you, it is nothing but the angle made by the regression line with the horizontal axis. E is the error term. This is our model. Y is equal to B0 plus B1x plus E is our model. So now why we are, and this is, then next thing which I have explained to you is how do we calculate error? We don't want positive and negative errors to cancel off each other. That's why we square them and then sum together to get our magnitude of error. But this is a very important concept in calculating in finding out our model. So we'll see that in the next slides. Okay. So now this is a bit technical. So be more attentive. See, x-axis can be any damn thing. Say x-axis can be our advertisement, radio advertisement. Say y-axis is can be any damn thing. It can be say marketing revenue. Okay. I have fitted a regression line here. So this is nothing. This is my regression line. This is my regression line which I have fitted. Okay. So now there are three terms which you have to understand. Residual term you already understand now. The difference between actual and y hat is nothing but actual. Y hat is a symbol we explain actually. Don't get worried by this symbol. Y hat nothing but actual value. So difference between observed value, actual value. Difference between actual value and observed value. Y hat is observed value. Sorry, I'm sorry for mispronunciation. Yi is actual value and y hat is this yi is actual value and y height is observed value. So difference between actual value and observed value, when we square it, it is called residual sum of squares that we have seen. Then what will happen, like if I give this kind of data to layman, he will not know that I have to fit a slant regression line. What he will do, he will just what you want projection, na? What he will do, he will sum up all the points and find out a mean. He will find the mean of x and he will find mean of y. So instead of getting model, like the most stupid thing will be to find a mean and draw this kind of horizontal line. So this is a horizontal line, right? This is the intelligent model, right? It is giving you some kind of projection. But if you don't, most stupid thing is to draw some, take mean of all the x, mean of all x, mean of all y. You take a mean and plot a horizontal line. Means you take a mean of all the observed values and say that this is my model. So this is most stupid thing one can do, right? If you do not have any mathematical tools, you do not have any computers, or you do not know coordinate geometry, then what you will do? You have so many points scattered all around. You will just find a mean. So finding a mean is the most stupid model one can make. So this mean line which is there, which I have plotted here, which are rounded off, this line, this we take as a reference line. This is the minimum we should do. This is the minimum one can do. So this we take as a reference model. So this mean line or horizontal line is nothing but our reference model. It doesn't change with x. For any value of x, value of y remains constant. It is a mean line. So this is our reference model. Slant line is our intelligent model. Okay. So we define all our terminology or all our calculation we do with the help of reference model. So reference model is what? Reference model is this mean horizontal line. Line horizontal to x-axis. Then what we do? Like how we find the actual value? Y hat is the predicted value of y given by x. Okay. Y hat is the predicted value that I was calling it as a observed value. Y hat is the predicted value of y given x in the equation. Okay. Yi is the actual observed value. Yi is the actual observed value. So this is actual value. And y bar is the mean value of y. So if I, for this particular point, if I draw a horizontal line, So this is nothing but this is my yi. This is my this is my yi. Yeah, sorry. So this is my yi because this is actual y belongs to this point. This is yi. This is observed value because this is given by this model. So this is y cap. This is y cap. And this particular point below, it is nothing but it is mean. So it is y bar. Okay. So like how much you have made your model intelligent. So your most stupid model is the horizontal line, and the intelligent model is your slant line. So how much you have come closer to the actual point? See, the actual point is this, which I'm plotting here. This is the actual point, your actual point. Your model is telling point as this as this point, which see here. So this is your model is telling this is the value, but actual value is this. And most stupid thing is telling actual value is mean. Mean is the actual value. So how much you have gone closer to the actual value, whatever is given by model. So this is called explained variance. This much gap between actual and you have to cover gap between actual and mean. So actual is y hat and mean is y bar. So in between is the observed value. So observed value is the gap which you have covered using your model. This is the value you got using model. So that means compared to the mean value, you have explained the variance by using the model. So what is explained variance? Y hat means observed. Y hat means predicted value minus mean value. Predicted. So see bottommost here, ESS. Little bit overwhelming. ESS is nothing but the predicted value minus mean value. So this much is the variance which you have explained. This much is the variance your model could explain. What is total variance? Total variance is nothing but total variance is between the difference between actual value and the mean value. This total variance is this. This is the total variance. This is the total variance. This which I am showing. This is the total variation, right? Most stupid thing is the main thing. Actual thing is this. So this we call as total variance. This we called as explained variance. This we called as explained variance. Why explained variance? Because between mean value and the observed value, you are able to still reach something better. This point which we see here, this point, this is still better than the mean value, right? So this is called explained variance. So explained variance, residual variance, and total variance. Little bit confusing for a newcomer. So I will stop here and I'll answer. I would like to, instead of me explaining, I would like to answer specific questions. So has everybody understood total variance? Total variance is nothing but the difference between actual and mean. Actual value means the top one, and the mean actual value means top one, and mean value means the horizontal one. Horizontal. This total variance, total vertical line is nothing but total error. This is our total error. Then difference between model and the mean. Model and the mean is our residual sum of square that we have already seen. And actual sorry, above. RSS I have not explained. RSS residual sum of square. Sorry, I am confusing you. RSS is nothing but some difference between actual and observed. So actual is this, where my cursor is. Actual is this. Sorry, actual is this, and observed is this. Actual is this, where my cursor is. Observed is this. This difference we call residual sum. Actual value is on this point, and between the mean we call that as a that point we call as a explained, that we call as ESS. And residual sum is what? Residual sum is the difference between actual and observed. So these three terms you have to explain. Three terms you have to understand. So can anybody tell me from the audience what is TSS, total sum of squares? What is the total error? How much is our total error? Can somebody tell me from the audience?
It is RSS plus ESS, the explained sum of squares and the residual sum.
Very nice. So can you explain it in qualitative terms? What is TSS?
So that means how far away are we from the mean?
Yeah, how much our actual observation is from mean. Very nicely
Actual
explained.
values away from the mean.
Yeah. Then can you explain RSS, residual sum of squares? Residual sum of squares. Residual sum of squares is nothing but you see the term residue. Residue means difference
Actual
between.
minus predicted.
Pardon?
Actual minus predicted.
Yeah, actual minus predicted is residual. Actual minus predicted is nothing but your residual sum of squares. And how much you could explain? How much difference you could explain? Total error is actual minus mean. So out of that, how much could you explain? So can anybody explain me what is ESS? Explain sum of squares. Explain sum of squares. Can anybody explain me?
Sir, difference between actual predicted model value and mean value.
Yeah. So difference between predicted value and mean value is the difference we could explain. So this is the intelligence we have developed by using our program, our model. So model has built up that much. Model has explained that much the variance. Total. Okay. So that is called difference between predicted and difference between predicted and actual is called explained sum of square. So as madam said, total sum of square is nothing but RSS plus ESS. So anybody would like to try? Anybody would like to take a shot and explain all the three to me? One person, single person should explain all the three. Can anybody explain? Madam, would you like to give a shot?
Yes, sir.
Yeah, madam.
So residual sum of squares is the difference between the actual point, the observation, and the model predicted one.
Yeah, great.
Model predicted one. Then
Yeah.
explained sum of squares is the difference between the model predicted one and the mean.
Yeah.
That variance.
Yeah.
So total would be the sum of both these. TSS.
Yeah. So
TSS is RSS plus ESS.
see, I want you to understand it qualitatively. Residual means बचा हुआ जिसको हिंदी में बोलते हैं ना, बच कितना गया. मतलब total कितना variance हमको explain करना था. How much variance I wanted to explain totally. So that is nothing but TSS. TSS is the difference between actual and mean. So this difference I had to explain. I had to explain this difference. I had to minimize this difference between actual and mean. I had to minimize. So how much I have minimized? So between predicted and mean, this much I have minimized. So what this I have predicted is y hat, and predicted is y hat, and minimum is y cap. So difference between predicted and y hat means mean. Predicted and mean difference between predicted and mean I have explained already. How much I couldn't explain? Whatever I couldn't explain is residual error. Residual error is difference between actual and predicted. Okay. So little bit confusing for a newcomer, but I think it is very simple concept. So why we learn all this? The value of ESS, if it is more, explained sum of squares is more. If ESS is more, that means our model is good. Am I correct or wrong? Okay, so let us see that. Let us leave that. We'll cover it later.
Sir,
Okay, in the
question
letters.
here. Sir, I have a question here.
Yeah.
So our algorithms, they try to minimize the RSS or TSS?
RSS.
RSS, okay.
Yeah. TSS is a phenomena, madam. You cannot minimize it. Your point
Yeah,
is there.
yeah, maybe the
And
data
your mean is
itself
also
so
there.
Yeah.
It is a phenomena. You cannot minimize it.
Okay,
It is given to you. RSS is what you want to minimize.
okay.
Ideally speaking, you want ESS to be equal to RSS. Sorry, ESS equal to TSS. You want RSS to be 0, right?
Yeah, right, correct.
So you want ESS to be equal to, TSS to be equal to ESS.
Yes, okay, I get
When
it.
whatever is the total error, you should be able to explain with the help of your model. So your RSS ideally should be 0, but it will never be 0, so it should be close to 0.
Okay, I get the
Okay.
point.
So
Yes.
ideally speaking, if you are a perfect mathematician, your TSS and RSS should be equal. But there will always be error, so we'll have some RSS also, and we want RSS as close as 0 to the possible. I think it is understood now. So simple again, the same equation in a more confusing way. Like equation of on the top is y is equal to mx plus c equation. You see this is simple our model equation. Error term I have not put. y is equal to mx plus c. Then what is our mean squared error? Mean squared error is a very important concept in regression. So mean squared error is yi is our actual, and y hat is, I'm substituting the value. Oh, so here something difficult. You look at this third equation, the third box, the dotted box. Okay. So yi, this is nothing but your actual value, and this is nothing but your predicted value, right? Because see, we have put the value from this equation, y is equal to mx plus c. For any given point I, I am putting the predicted value mxi plus c. So yi is this is your which I am telling, this is your actual, and this is predicted, right? So difference, we take difference between both, square it and divide by the number of observations, number of points, how many number of points we have, we divide by it. So this is called our mean squared error. Why mean squared error? We are finding out the error, summing up all the error for all the points, and then we are finding a mean. So it is called a mean squared error. Simple. So this mean squared error is a very important metric in our regression calculations. So now somebody should tell me, other than madam, whether you want to minimize mean squared error or you want to maximize mean squared error. Anybody? Anyone from Gesu guys? You want to minimize the mean squared error or you want to maximize mean squared error?
Sir, minimize.
Why minimize? Because it is representing an error term, right? So you want to always minimize error, right? So you want to always minimize mean squared error. So if one model is having a mean squared error of 100 and another model is having mean squared error of 10, so that second model with mean squared error is 10. Model with mean squared error is 10 is better than 100, and mean squared error has no units, it is no unit, right? What is it is the difference squared and divided by n. So it's a simple number. So if you want to compare two models, simply calculate mean squared error of model 1, mean squared error of model 2. The model with lesser mean squared error is called a better model. So it is all comparative. So mean squared error is always, short form is MSC. Okay. So it is, remember, like nobody will tell you it full form as a mean squared error. It is always called MSC. Okay. So then I don't want to go into math. So like somebody rightly said, this equation is there, right? This equation E is equal to 1 upon n sigma of I is equal to 0 to n y actual minus y predicted. So this equation is there, and somebody rightly said from our student community that they want to minimize this. Minimize this means what? They have to take a partial derivative of this. Partial derivative should be taken, and that partial derivative should be partial derivative with respect to what? It is a variable of x. See, it is a variable of x. So mx yi minus mxi plus c. So x is a variable here, right? So you have to take partial derivative with respect to x and minimize it to 0. So once you minimize this equation, then you will get this kind of curve. This curve you see. You see this curve. So you will get this kind of parabola. It is nothing but it is close to equation of parabola, right? It is a squared equation. It is a squared equation means of the order to the power 2. So it will be equation shape will be like this, parabola shape. If you know the equation of parabola. So equation of parabola is something like equation of a parabola. If any, I don't remember the equation of a parabola, but okay. Anyway, it is having squared terms. So this will be like you are a valley shape, U shape. So it can be equated to a valley. It is equated to a valley, and one mountaineer, like a Parvatarohi mountaineer, we call the mountaineering guy. So one mountaineering guy is descending this valley. So when we find a partial derivative and equate it to 0 means we want to find the minimum of this curve. So when we find the minimum value, this value when we find when we find, then it is that will determine the value of M and C. So we are not going into the math. why we are doing it? We are doing to find the value of m and c. We just equate this error term, we differentiate with respect to once we differentiate with respect to m, equate it to 0. Find the value of m. Another time we differentiate it with respect to c and then equate it to 0. Okay, so I'm sorry little bit for creating bit confusion. Here the variables are m and c, not xi and yi. Yi and xi are concrete values given to you. These are points, values given to you. Here in this equation, variables are m and c. So this error equation, once you will differentiate with respect to m, equate it to 0. Second time you will differentiate with respect to c and equate it to 0. So thus solving that you will get the value of m and c. And once you know m and c much, you can very easily fit into this line and you get your model. So this is the process of getting this model. Okay, so if you plot this mean squared error, it will be a curve like this. The white curve we have shown. It is like curve like this, and our objective is to find minima of this curve. So why we find minima? To get the value of m and c. Okay, m and c. To get the value of m and c. Why we need m and c? If we have m and c, then we have the complete equation. We have the equation means we have our model. So I think some equation points are there. If somebody is interested in the more deep into maths, come to me after the class. I will explain it to you. Okay. Now some very interesting thing I want some very interesting measure we are finding. How to measure a model? One way is to measure with mean squared error, right? Like with respect to mean squared error, you can measure. But mean squared error is not an absolute measure. One model, you can compare models with the help of mean squared error. This model with more value of mean squared error is bad. You can compare, but you cannot tell that if I have mean squared error of 10, then it is good, or it has 20, then it is good. Because some problems may have errors in hundreds. Some problem will have mean squared in thousands, right? And some problem data sets can have mean squared error in lakhs also. So you cannot say which mean squared number, which absolute number is good. You can always say that MSE of 10, MSE of 100. So model 1, model 2. So model 2 is better than model 1. You can tell this, but you cannot tell that in this universe, whatever model I will have, a model with a value of 10 will be good. You cannot say that, because all the data which you get in data sets is on a different scale. So mean squared error will always vary depending upon data set. Mean squared error will always vary. So for a given data set, model with less mean square error is better. So listen it carefully. For a given data set. So for a given data set, what is very important? For a given data set, a model with lesser mean square value will be better. Understood na? Matlab Hindi, if I want to tell it in Hindi, any model जो भी model जिसका mean square value कम हो, it will be better. But with respect to what? It will be there for that data set only. For a different data set, the scale of mean squared error will be different. Understood na? Scale of mean squared error will be different. So we need a model measure whether data set 1, data set 2, data set 3, or any number of data set. Simply by reading that model, reading by the value of that measure, I should be able to tell whether this model is good or not. Okay. So suppose I will give you an example like BTech. There are 5 students in BTech. Somebody got 80%, somebody got 90%, somebody got 70%. So you will take 90%. The guy who got 90% is studied better. Okay. So this for a class. Okay. So you can say for a class, the guy who studied got 90% is better than the guy who studied with 70%. He studied better. He may not be absolutely better, but he studied better. Now, what about, suppose you take a class of MBA, and you are getting the same data, 3 students, one student with 90% marks, other student with 80% marks, another student with 70% marks. But in the MBA class also, you can tell that the boy who got 90%, studied better than the guy who who got 70%. So we cannot compare BTech class and MBA class, but still with the percentage is such a measure, with that we can tell which student is academically better, right? So similarly, mean squared error is for a given data set, but we need a measure, such a measure that for any data set, that value should be able to tell us whether model is good or bad. So R squared, there is something called R squared. There is something called R squared. So don't go by R squared. R squared is, this is not R squared, R square of the R. It is not square of the R. It is simply called R squared. And why it is called R square, I am also searching why it is called R square. So I am also searching for it. Maybe sometime I have to Google it. So R square is a simple term. It is not, it doesn't mean square of R. Mathematically, it doesn't mean square of R. We simply call it R square. R square is nothing. It is a model metric. Metric means measure of model efficacy. It is a metric which tells how good or bad the model is. It is 1 minus residual sum of error upon total sum of error. So when I was explaining you RSS and TSS, I explained you that ideally we want RSS to be 0. Put RSS equal to 0 in this equation and tell me what is the value of R square. Anybody? Put
1.
the value of RSS as 0 and tell me the value of R square.
1.
1, right? So then we tell that when value of RSS 0 means the best model, right? RSS 0 means best model. And if I put RSS as 1, if I put RSS as equal to 1, then what will the value of R square?
0.
0, right? So RSS equal to 1 means you are not done any model. You are not done any modeling. Your total sum of square and your TSS and RSS are equal. So you are not done any modeling. When you do any modeling, your RSS will be less than 1. Your RSS will have some value. So RSS will always be less than TSS because your model is explaining something. So RSS upon TSS will always be a fraction less than 1. Right or wrong? 1 minus RSS upon TSS will always be a fraction less than 1. And we want RSS to be as small as possible. So for a good model, RSS upon TSS will be very close to 0. So when you deduct a quantity very close to 0 from 1, you will get something like that 0.98, 0.97, 0.99, right? So any value of R square which is more closer to 1 is called good. So in absolute practice, when data science professionals talk, any value of R square above 0.8 is acceptable. 0.8 it is sometimes they call it 80% also. 0.8 fraction they call it 80%. 0.9 they call 90%. So any R square above 80% is acceptable. 0.9 any R square above 0.9 means 90% is very nice. And by like very bare minimum you need R square above 70. Below 70 nobody will accept. Even below 80% nobody will accept. But if you want to go to lower limit, you have to give some model which is close to 70%. Okay, so that's where R square is. So for data set 1, I am calculating R square. For data set 2, I am calculating R square. Data set 1, I am making model, calculating R square. Data set 2, I am calculating making model, calculating R square. Data set 3, I am making a model, calculating R square. Okay. So all the 3 I can compare now. If R square is close to 1, model is 1, model is good. But mean squared error I can compare within only that data set. Within that data set, for that data set only I can compare model 1, model 2, model 3. For that data set only I can compare if I use mean squared error. But if I use R square means I can always tell. I can compare for any data set. I can set which model is good, which model is bad. So this is a very simple percentage, nothing but a simple percentage kind of measure. So once again I will explain you what is total. TSS is total sum of squares. It is nothing but actual minus mean squared. Actual minus mean squared. Residual sum of squared is nothing but actual minus predicted squared. Explained sum of squares is nothing but Explained sum of squared sum is nothing but predicted minus mean squared. Now I will give you one gift, like I'm sitting remotely, but I will give you a gift if somebody tells me, somebody removes this r out of this one out of this equation. We have 1 minus RSS upon TSS. I want to remove this one and re-express this equation.
Sir, we can take LCM.
Then what you will do with LCM? Then what will be the numerator? Then
Sir,
what will be the numerator?
Sir, TSS minus RSS upon TSS.
TSS.
Okay, then what is
ESS
TSS and
upon
minus RSS?
TSS.
ESS.
ESS upon TSS.
Yeah, exactly. This is what I wanted. So R square is nothing but ESS upon TSS and other terms. Explained variance upon total variance. Very simple, na? Total variance is something 100, and how much of that you have explained is on the numerator. So how much your model good is in the numerator, and what you want to do is in the denominator. So very simple. Explained upon total. So explained error upon total error. So this is what your R square. R square to the close to 1 is the best. This is very easily understood. Now you understand why visually looking at the plots itself, you should be able to take what is the value of RSS. See, in the first plot, in this plot, what is the speciality of this graph? Anybody? What is the speciality of this graph? What is the speciality?
The line fits exactly as per the data points.
Yeah, so when line fits 100%, then it is R square equal to 1. What about the second which I am drawing here? Second one. It fits, but somewhat fit, not exactly, but close to fitting. Okay, it is fitting, but not very exactly. So it is R squared 0.70. Now you see third one, this one, third one. You see all points are scattered around all over. The fit is better than second one. Third one, it is even worse. Okay. So it is R square equal to 0.36. And 3, the fourth one, this one. There is no fit at all. It's a random points. Points are randomly fitted all over, so this R square is close to 0.05. So why I have given you this, by seeing nobody will ask you to give value of R square. But as a seasoned machine learning professional, by looking at the graph itself, error graph, this is nothing but error. No, these are points and model. So simply by looking at the observed points and the model, you should be approximately able to tell the value of R square as a seasoned professional between say plus minus 5%. So understood, R square 1 exact fit, R square 0.70 means this kind of fit, somewhat fit. 0.36 means fit is even worse, and 0.05 means there is no fit at all. Points are scattered all over. So this is just wanted to give you a feel of R square. It is a very important measure. And RSS, I am once again explaining you, it is nothing but actual minus predicted. For every point you calculate actual minus predicted, square it and sum, it is RSS. I am explaining once again. You want to minimize RSS. Okay, now you have error terms like E1, E2, E3 up to En. E1 means for 0.1, what is RSS? E2 means 0.2, what is RSS? En means for point n, what is RSS? You will be given n number of points, n number of points in the historical data to find out your model. To find out your model, you will be given n points. So for first point, E1 is the error. For second point, E2 is the error, and for nth point, En is the error. So now there is one thing we have seen. R square should be close to 1. Okay. But there is another measure also. The error should be equally distributed around the vertical axis. So you see here, I have just taken error E1, E2, E3 like y train minus y predicted. Y train is nothing but actual point. Y train is, this is actual point. This is actual point. This is actual point. This is predicted point. Actual minus predicted. I have taken, plotted here. And then I have plotted for point value of, say, you take very value, minus 0.75. I have not squared it, okay? I have not squared it. So just for negative value of my minus 0.75, how many occurrences are there? So probability of occurrence I have plotted. So I have basically plotted a basic histogram. So histogram should be near to a bell curve. Near to a bell curve. It can be perfect. It can be never perfect bell curve, but it should be near to a bell curve. So this should be nicely distributed. Histogram of error, if I plot, it should be nicely distributed. Now it should be bell curve. This is one. It is one very vital condition for your model to be valid. Linear regression model to be valid. Okay, it is a very vital condition for your linear regression model to be valid. I'll explain you why. And another thing is, this is one condition. Histogram you can plot with just half a line of command in Python. You have minus 0.5, minus 7.5, 5, minus 2.5, 0, 2.5, 5, 7.5. Just put it in a list or array, and with one command of matplotlib or C1, you can plot this histogram. So it's no big deal to plot a histogram like this. Okay. So you plot histogram, and histogram should be near to a bell curve. So at home, you should go home and take it as a homework to study what is histogram. Because if I ask question, many of you will not be able to tell me what is there on the y-axis. Can anybody tell what is there on the y-axis? If somebody tells, means they remember their high school statistics very well. Can anybody tell what is there on the y-axis? What is 0.02, 0.06, 0.01, 0.16, 0.08? What are these values? X-axis I have explained already explained to you. It is already error term. But what is y-axis?
There's probably the frequency. Like
Yeah,
how many?
it is not the frequency. It is the probability.
Oh, probably.
Probability density, like probability of finding number of times number of times minus 7.5 times occurring divided by the total number of records. Okay, so frequency of minus 7.5 divided by total frequency. That is what is on the y-axis. Understood what I am telling?
Yes, sir.
Frequency of minus 5.0, frequency of minus 5.0 divided by the total number, the total frequency. That is what is plotted on the and histogram is a very basic it is called normal distribution. It is called normal distribution, and it is one of the very basic requirements before you even pick up the book of machine learning. So I want you guys to go home, take it as a homework, see what is histogram and what is normal distribution. Note down 2 homeworks. I will ask this next class. Number 1, what is normal distribution? Number 2, what is a histogram? Number 3, what is a bell curve? These 3 terms you should Google and find it out. Number 1, what is normal distribution? Number 2, what is a histogram? How it is drawn? What is a histogram and how it is plotted? And number 3, what is a bell curve? Very simple. Within 5 minutes, you will be able to find out. But make your concepts clear. Otherwise, it will be tough for you. Like you will be able to do my course now, not a problem. But in interviews and all, you will not be able to clear interviews unless you have your concept clear. So that's why I'm giving you this small homework. So now you see, apart from this bell curve, there is one more condition, that we just take error terms on the y-axis. I have plotted error term. Here is y-axis is there. You see y-axis here. This y-axis. This y-axis. This is the vertical axis. Okay. So what I am plotting here, I am plotting error term E. Both positive and negative I am plotting. Positive also plotting, negative also plotting. I am not squaring it. I am plotting positive up, and I am taking a mean line like this. This mean line I am taking. Negative I am plotting below and positive I am plotting below. So these are error terms. So if I calculate n error for n number of points, if I calculate n errors for n number of points, my plot should not be this, looking like this. My plot should not be looking like this. My plot should be looking like this. So can somebody tell me what is the difference between first, second and third one? Why third one is different than 1 and 2? Can somebody tell me?
First two has some symmetry there.
Yeah. And what is third one?
Third one do not show any
symmetry in error terms, right? So it is randomly distributed.
Random.
Great. Very nice. Thank you. So if any pattern is there between error, if you are plotting error terms here, right? So if you see any kind of pattern, these are only two patterns I have shown you: vertical U and like inverted U and vertical U, or like simple VU and vertical, simple and inverted U's. I have plotted. Any type of pattern you see, these is the only two patterns. Any pattern you see, any kind of pattern, then your model, you need to have a relook at your model. But if error terms are randomly distributed like this, no, showing no pattern, just random distribution. See, this is also a random distribution. This one also is a random distribution. But these are observed points. These are observed points. These are not errors we have plotted. Here we are plotting errors. So errors should be randomly distributed. Okay, so these three things should be there. Our R square should be close to 1. Our error histogram should be close to a bell curve, very symmetric, and error term should be randomly distributed. So these are the three conditions, three checkpoints whether our model is good or not. Now with this, I have not explained you one thing. Which is some assumptions. We take some assumptions before making the making the model. When we make linear regression में इसको बोलते हैं ना linear regression के नखरे बहुत ज़्यादा है. हिंदी में बोलते हैं ना linear regression के नखरे बहुत ज़्यादा है. It has some prerequisites, some conditions to be satisfied before we can call our model to be correct. Okay, so these assumptions I have not told you so far. So I will tell you assumptions, and then we'll do a simple coding problem. How much is the time? It is already 5. We started at 4 p.m. now. Okay, so I want to tell you the assumptions of linear regression, and then I want to explain you one code problem.